Hi everyone, welcome to our seminar after the winter break. It's my great pleasure to introduce our first speaker this semester, Marta Strzelecka from University of Graz, who's going to tell us about norms of random matrices. Marta, please.
Thank you, Tomasz. Hello, everyone. It's really nice to see all of you, and welcome for a new semester of probability analysis webinar. I would like to thank Tomasz and all other organizers for keep organizing these meetings. So today I would like to tell you about norms of structured random matrices, about a certain conjecture which we posted in our joint paper with Radek Adamczak, Josza Prochno, and Michał Strzelecki. And I will also present one of our results and try to give you a proof. So let us begin with a setting we will be working with. We have two parameters P and Q between 1 and infinity, including infinity, and we will consider LP spaces which are equipped with a standard LP norm. We also have a deterministic real M by N matrix A with coefficients Aij, and a random Gaussian matrix of the same size, G with entries Gij's, which are independent standard Gaussian random variables. And by G with subscript A, we denote the Hadamard product of A and G, which is simply entry-wise product. So the entry of G with subscript A is Aij, Gij, the deterministic Aij and random Gij. And we call such a matrix the structured Gaussian matrix. Our aim for today is to find the quantity which is comparable with expected norm of expected value of the norm of GA, treated as the operator between LP and LQ. And this quantity should be comparable up to constants depending on P and Q. So we denote this approximate equality with subscript PQ if we allow constants depending on P and Q. And we would like to have this quantity which depends only on the coefficients of this matrix A, only on Aij. So in other words, we would like to find a function f which depends only on the matrix A, such that our expected norm of structured Gaussian matrix is comparable both from above and from below with f of A up to constant C depending on P and Q. So we'd like to have such the inequalities. And then we say that this expected norm behaves like or is comparable with this quantity. So now I would like to present you a conjecture and try to convince you that it should be true. I will also say when it is true, when it is known it's true, and show you this theorem which says that it is true up to constants which depend logarithmically on the dimensions n and m. So they are not only the constants depending on P and Q, but multiplied by some logarithm of the dimensions. Okay, so let me introduce with what was known before. There's a theorem by Latała, von Handel, and User from 2018, which is very important and solves the problem posed by Latała many years before. So they proved that in the case when both P and Q are equal to 2, so when we deal with the spectral norm of our structured Gaussian matrix, this expected norm is comparable with expected norm of maximal column plus expected value of maximal Euclidean norm of row of the matrix G with subscript A. So this is not our desired quantity, because we wanted to express this only in the terms of the matrix A, but it is comparable, which was proven before by Van Handel, that this quantity is comparable to such an expression, which is not so important to know what it exactly is. For us, important is only that it depends on the coefficients of the matrix A. So it's not so important to know what this Aij star are. There is also another form. This is comparable to maximal Euclidean norm of columns of the matrix A plus maximal Euclidean norm of rows of the matrix A plus expected value of the maximal entry of our structured matrix. So this expression is more handy than this ugly with stars. This one ugly with stars. So we'll keep writing everything with such a term. And you should only remember that every time when it appears, it may be, and it's added to some maximum of some norms, not necessarily Euclidean norms, but some other norms here and here. Then it may be comparable with the same two terms plus this guy, which depends only on the coefficients of the matrix A. So every time when we see this term, it's good. It may be written differently. So we see a quantity which depends on the coefficients of the matrix A. Okay, so they solve our, they give the exact behavior of our expected norm in the terms of coefficients of the matrix A when we have P and Q equal to 2. What happens in other cases? When P is less or equal than 2 and Q is greater or equal than 2, Gedon, Hinrichs, Litvak, and Proto proved that this expected norm of structured Gaussian matrix between LP and LQ is less or equal up to constants depending on P and Q and up to some logarithm. It is less or equal than this expression. So let us compare it with what we had before. Here, instead of the Euclidean, maximal Euclidean norm of columns, we've got the P star norm, because now we go from LP instead of L2. Here, instead of maximal Euclidean norm, we've got maximal Q norm, and the third term is the same. So it's a kind of weaker generalization of the previous band. Surely we've got this logarithm here, which is probably very, very removed from such a band. But at least this works for P less or equal than 2 and Q greater or equal than 2. And moreover, the lower band also holds. The red guy, the green guy, and the blue guy are the lower estimates for our expected norm. So it's natural to conjecture that in this range, when P is less or equal than 2 and Q is greater or equal than 2, the sum of color guys, red guy plus green guy plus blue guy without logarithms is the exact behavior of our expected norm. But what for other P and Q? Then it's we should write red and green guy in a more handy form for other P's and Q's. So the red guy in this range is equal exactly to this. So what happens here? We've got A circ A. This is Hadamard product of A with itself. So its entries are simply Aij squared. And this is the norm as the operator from LP halves to LQ halves. And everything is raised to the power 1/2. This is because we need to keep the homogeneity. And the same with this green guy. It may be written differently for P between for P less or equal than 2 and Q greater or equal than 2. And the advantage of such a representation is that now red guy and green guy and also blue guy are the lower estimates for our expected norm for every P and Q between 1 and infinity, even outside this range. So again, it's in, and moreover, our theorem, as you will see, proves that the sum of colorful guys multiplied by some logarithms is also the upper bound. So it seems natural to conjecture that their sum, the red guy plus green guy plus blue guy, are the exact behavior of our expected norm. So that this expected norm of structured Gaussian matrix is comparable to this sum. But the truth is more complicated, as you will see in a moment. So let us call this term D1 and this term D2, and I would like to convince you that our expected norm of structured Gaussian matrix for a given P and Q should behave like D1 plus D2 plus something else. And this something else will be presented on a diagram. So here we are with the diagram. We would like to have, as I mentioned, this expected norm to be up to constants D1 plus D2 plus what? On this diagram here, on this axis, you've got the reciprocal of P. So P equal to 1 is here, P equal to infinity is here at the origin. And on this axis, you've got reciprocals of Q. So Q equal to 1 is here, Q equal to 2 is here, and Q equal to infinity is here. This point is when P is equal to 2 and Q is equal to 2. And this diagonal represents what happens when you use the duality. So for every matrix, not only GA, you know that the norm of GA between LP and LQ is equal to norm of GA transposed from LQ star to LP star, where Q star, oh, I should mention it before, sorry. This is the Hölder conjugate of Q. And the GA transposed, by the definition, is the random matrix G transpose, so of the sizes n times m, with a structure A transpose. So if you have this estimate, D1 plus D2 plus something, in, for example, this point, for every structure A, then you also have it on the opposite side of this line, of this diagonal, here, just by duality. But D1 plus D2, their dual versions are exactly D1 plus D2. So you should also take the dual version of this third term. So by duality, you may substitute P and Q by Q star P star. Okay, so what we know, let me recall it, by this result of Gedon, Hinrichs, Litvak, and Prochnow, we know that this third guy is probably equal to expected value of maximal entry of our matrix, and by up to logarithm is confirmed in this square, and they also prove that on the boundary this conjecture is true. And we also know that in this point, by the result of Latała, von Handel, and Józef, our expected norm behaves exactly like D1 plus D2 plus this term. What outside? So in our work, we proved that on this part of the boundary and on this part of the boundary, this expected norm behaves like D1 plus D2 plus this quantity. And what is Bj star? Bj, B is a vector whose jth coordinate is equal to this norm of the cone of A. And Bj star has the same entries as Bj, but permuted in such a way that they are non-increasing. Okay, and the same with di star. This is a kind of dual version of this quantity. And on this part of this boundary, we prove that there's the third term is not needed, so that our expected norm behaves exactly like d1 plus d2. Okay, so since we have lower bounds on this part of the boundary, it's easy to generalize this lower bound to this whole trapezoid, blue trapezoid here. So we've got lower bounds here with this term. And on this trapezoid also, we've got lower bounds with this term. So it's natural to conjecture that maybe what is drawn on this diagram is the exact behavior of our expected norm. But something else happens. No third term is needed in this huge yellow triangle, since for every P and Q from here, you may bound this term by the sum of d1 plus d2 up to constants depending on P and Q, and the same here in this old trapezoid, where whenever you are in this yellow area, you may bound this term by d1 plus d2 up to constants. So no other term is needed everywhere here. Okay, and you may ask, what happens if you take the point from this small blue triangle? Maybe this term may be also beaten by d1 plus d2 or d1 plus d2 plus this expected value of maximal entry. But the truth is no, not by them. If you take any point from this triangle or any point from this triangle, then you may find a certain structure A, the deterministic matrix A, such that our expected norm with this structure is of the larger larger order than d1 plus d2 plus this term. So it seems that you may not easily beat this third term in this form, in this area. So this is why we conjecture what's written here. Here you've got the definition of d1 and definition of d2 from the previous slide. And this term is the term from the small red square. These terms are the terms from small blue areas, and this term is from this large area where nothing else than d1 plus d2 seems to be needed. And once again, we confirm this conjecture everywhere on the boundary. And for the case P equal to 2 and Q equal to 2, it follows by the theorem of Latawan van Handel and Joseph. And we have the lower bounds everywhere and upper bounds up to constants. So the question is, does this conjecture hold for other P and Q in between 1 and infinity? So do you have any questions by now? Okay, so I will move to this theorem, which shows the lower bounds up to logarithmic terms. So if we have any P and Q between 1 and infinity, then expected norm of structure Gaussian matrix from LP to LQ is less or equal up to some constant, which even doesn't depend on P and Q. Logarithm of n in the power 1 over P star, logarithm of m in the power 1 over Q, and d1 times square root of logarithm mn, d2 times square root of logarithm of n. Okay, so it's quite easy to deduce from this theorem its counterpart for other structured random matrices. instead of G, we take now X, which is a random matrix with independent mean zero entries, which satisfy psi-R condition for R between 0 and 2. So we assume that probability that absolute value of Xij of every entry is greater or equal than T is less or equal than some constant times e to the power minus t to the power R divided by another constant R. And then we've got a similar band as for in the Gaussian case, up to constants depending on only on R and these constants K and L times this quantity, D1 plus D2 up to some logarithms. This is the new term in this band. We've got logarithm of mn to the power 1 over R minus a half. So in the case when R is equal to 2, when you have sub-Gaussian entries, then you have exactly this band up to some other constants. The same as in the Gaussian case. And for example, if R is equal to 1, for example, for concave random entries, then you have another square root of logarithm in this band. Okay, so let me show you the proof of our main theorem. We will need this lemma, which will be crucial in our proof. Assume that P sits between 1 and infinity, and n is an integer, which will be our dimension. And we defined a convex set, a convex hull of points of this form. We take any non-empty subset of all first n integers, and our point has support exactly equal to j, and on every coordinate from this support, it is equal plus or minus. It may differ on every coordinate. 1 divided by the size of j to the power 1 over p. So it is rescaled in such a way that all these points sit in BP. And then our lemma says that BP n is not only L is not only contained in BPN, but BPN is also contained in L multiplied by logarithm En to the power 1 over P star. So when we use our lemma in our theorem, then we see that this norm is surely supremum over all x's in the unit ball of this space. So in BPN, this is the unit ball in the LPN space. Supremum over all points from the unit ball in the dual space of LQM, so BQ star M, of this double sum. So instead of taking x's in BPN, we may take x's which sits in logarithm to the power 1 over P star times L, and then this constant logarithm comes here in front of our suprema, and here we have x's only in L, but since this sum is linear with x, we may consider only x's in the extremal points of L. And extremal points of L are exactly points of this form from the definition. And the same happens with y. So when we write every point of extremal points of L in such a way like here, we have maximum only on all possible supports of points x. So no non-empty subsets of the first n integers I, and all j, which are non-empty subsets of all first integers, n integers, and maximum over all choices of signs. And you divide by the size of the set I to the power 1 over Q star, and the size of the support of of the point x to the power 1 over p, and you sum up only for i's in I and only for small j's in j of this sum. You see here, you see only the signs because this constant comes in front of the sum. Okay, so we will do not need this lemma anymore. And instead of writing those logarithms, we write only logs. And here we've got maximum over all subsets. So we treat separately the subsets of the given size. So we take the maximum over all possible sizes k of subsets I. So k is greater or equal than 1 and less or equal than m. And then the size of I to the power 1 over q star is just k to the power 1 over q star. And the same with j. J is always equal to L, and we take maximum over all L less or equal than M. And here you've got maximum over all subsets, which are exactly of the size K. And the same with J. And this is written as it was. Okay, but here this maximum is equal exactly to this supremum, because the points of the eta is all the points eta which coordinates are equal plus or minus 1 are exactly the extremal points of this of the unit ball in L infinity space, and the same with this epsilon j. So instead of epsilon I, we've got yi from we do not have a star here. We only have y in b infinity and x in b infinity. So we should estimate the expected value of this whole expression. So expected value of this maximum over all k and L, but by a standard tricks with Gaussian concentration, it suffices to estimate the expected norm of this orange expression. So if we have time at the end, I will show you how we may use our bands if we have the expected, if we can estimate expected value of this orange expression, and if no, it is only a standard. So let's move to estimating this orange expected value of this orange expression. So by Gij tilde, we denote an independent copy of the matrix Gij. So then the expected norm of our expression by the duality supreme over all y's in B infinity is just the L1 norm of this sum treated as the vector in coordinates of I. So it is equal exactly to this. This is the first norm. Then by triangle inequality, you may put a constant expected value of this sum inside Supremum, and you have to write it again outside Supremum. But by the Jensen inequality, you may move this expected value outside and you lose only inequality here. So also this inequality is true. And according to this, when we want to estimate this expression, you may only use that this random variable inside this absolute value has the distribution like the Gaussian random variable with mean 0 at the variance sum of aij squared xj squared over all j in j. So this is just expected norm of a single Gaussian random variable times this variance. And this green expected value is equal exactly to square root of 2 over pi. So this is a constant. And if we take supremum over all x's in B infinity, so every coordinate should be less or equal than 1, and you've got xj squared here. So this is the biggest if all xj are equal to 1. So you may just erase this xj and this supremum. So it happens here in this last inequality, last equality. So this term is good. It depends only on the coefficients of aij as it was promised. And we should take care only of this blue one. So how to estimate it? Note that that these quantities indexed by subscript I are independent and all symmetric. So our blue guy is equal exactly because there is the equality of the distribution of this random variable and this random variable. By the same, but multiplied by epsilon I, and here epsilon I are independent random variables which are centered, which are plus or minus 1 with the same probabilities because they are centered. So they are independent Rademachers, which are also independent of every other variables. So by triangle inequality, this is less or equal than the sum of expected value of suprema of the sum of this guy plus expected value of suprema plus the sum of this second term. But they have the same distributions, Gij and Gij tile. So you see twice the same. And instead of writing the sum of all small i's in the set I, we may write the sum over all possible i's from 1 to m and put the indicator set of the set I sits in I here or equivalently here inside. Now we will do not need, now we won't need this, this gray expression, so it disappears. And instead we've got the lemma, which is called contraction principle, which we would like to use in a moment. So let me recall it. When T is a bounded subset of Rm, like for example, what is written here, and we assume that phi I are 1 Lipschitz and equal to 0 and 0 for all i's, then expected norm of suprema over all points T in T of sum epsilon I psi I Ti are bounded from above by the same but without this psi I. And would like to use this lemma with psi I all equals to the absolute value of the point T, which are surely 1 Lipschitz and equal to 0 in the 0. And for Ti equal to this sum, which is marked in blue. So using this, we may just erase this expected value here. And we've got this inequality. So now the contraction principle is not needed, so it will disappear in a moment. And we go further. So epsilon I times Gij have exactly the same, this matrix, epsilon I Gij has exactly the same distribution as simply the matrix Gij. So we may no longer write this epsilon I here. So what we have just proven is that expected norm of this orange expression is less or equal than this quantity, which we like, because it depends only on the coefficients of of the matrix A, plus twice expected norm of something similar to this orange, but without the supremum here, and without this y's here. So the dependence on these y's disappeared. So using the same reasoning, we may also get rid of this supremum over all x here and xj here. But then not this term appears, but it's dual version when we have the sum over set j outside and the sum over set y inside this square root. Okay, so putting these two things together, we got this expected norm is less or equal than some constant times this term plus some constant times this term plus 4 times this expected value. So now we should estimate this expected value somehow. So let us call this double sum by xij. So this is a certain Gaussian process in indices by the sets I and j. So let me recall that I were were the subsets of the first m integers, which are of the size k, and j were the subsets of all the first n integers of the size L, and we've got xij, which is Gaussian process. So how can we estimate supremum of the Gaussian processes? We may use Slepian's lemma, which says if we have two Gaussian random processes or random vectors, which have the same mean, and the variance structure of x, by this I mean expected norm of xs minus xt squared for all s and t in t, when this variance structure on the set t is less or equal to the variance structure of the process y, then expected value of supremum of x may be bounded from above by expected norm of supremum of the same set of the process y. So we may compare Gaussian processes using Slepian's lemma. And we would like to compare our process x from the previous slide with this process y, which is indexed by the sets y and g. And here ji are standard Gaussian random variables. Gj tide are also standard random independent standard random variables, which are independent also of the whole vector g. So g is independent of g tide, and it's very easy to estimate expected norm of supremum of y. So this expected norm of supremum of this blue term is less or equal than expected norm of maximal absolute value of gi times supremum of this sum. And the same happens with this expected norm of supremum of this green term. And expected norm of maximal absolute value of Gaussian is comparable to square root of logarithm m, and the same happens here. So we may estimate expected norm of supremum of y by the quantities which are satisfying for us times some logarithms. So and please note that this vector is centered. Its expected norm is equal to 0, and the same happens for our process x from the previous slide. So we only need to check this condition. So for vector x, its Gaussian structure is equal exactly to expected norm of xij star plus expected norm of xi tide j tide squared minus twice the mixed term. And this first term, by the independence of the gij's, is equal exactly to the sum over all small y's in y, small j's in j, which we omit this small I and small j, aij star, and similarly with this term, and this twice the mixed term is the expected norm of this sum times this sum with I tilde, j tilde, and the only terms which survives the expected value is are these when we multiply gij by the same gij. So we have to keep in mind that I sits in I, and also it sits in I tilde. This is why we sum only for i's in the intersection of capital I and capital I tilde, and the same with j's. And we may write it in a different way. Here we have twice the same sum. So the first sum we write like minus the first sum, we write like minus this plus this. So this is only the set theory. And the second minus sum, we write like minus this sum plus this sum. So the sum over j tilde, and we have to add j tilde set minus j to have only the intersection of j and j tilde. And what happens with the variance structure of the set of the process y? So again, it's expected this expected norm is equal exactly to this, and this term gives us twice sum over y and j of aij squared. The first sum comes from here, the second sum comes from here, and there is no mixed term because they are independent. The same happens here with this expected norm, and this mixed norm is equal exactly to this. So we do not have the mixed term like that. From here we take the first sum, and from here we take something from the second sum because they are independent. So we only take this guy multiplied by this guy with the sets I tilde and j tilde. And using this simple inequality, we see that minus twice this sum is greater or equal than minus this sum and minus this sum. And the same happens here. So now when we take one of the sums from here and join it with this sum, we will see only the sum of aij over the set I and j minus j tilde. And the same here. We take one of the sum from here and join it with this sum. And we end up with I tilde and j in j tilde set minus j. So this is what we've already calculated. We know that the variance structure of y is greater or equal than this, and the variance structure of x is equal exactly to this. So the first four terms are the same, and here we sum over the larger sets. We sum something which is non-negative, aij star. So this sum is greater or equal than this, and this sum is greater or equal than this. So the variance structure of y is indeed greater or equal than the variance structure of x. And by Slepian's lemma, we know that expected norm of this orange expression is less or equal, you remember, less or equal than this sum plus expected supremum of the set x, which is by the Slepian's lemma, by Slepian's lemma, bounded by expected supremum of the process y, which is equal, which may be bounded by this. So this is what we wanted to prove. Now you have to recall what this orange expression was and how it was related with our expected norm of structured Gaussian matrix, and make some additional calculations, but you end up exactly what was on the right-hand side of our theorem.